Hi, this is Rob Anthony. Welcome to the premiere of Josephson Junction TV. We've got fresh new stuff coming up here. So the first thing the viewer may be wondering is, what is a Josephson Junction? Well, a Josephson Junction is two superconductors with a non-superconductor sandwiched in between them. And these are very small. They're nanometers to micrometers on scale. So the cool thing about Josephson Junctions is, if you put a small bias current through them, you'd expect there to be a voltage drop across the Josephson junction because there's this non-superconducting piece in between it. But due to quantum mechanics, there can be tunneling, and there's actually no voltage drop, so the whole thing just acts like a solid superconductor for small currents. Once you get above these small currents, then you start to see a voltage drop that oscillates like an electrical oscillator. So that's what we're studying. So why would you be interested in these things? Well, the main application is going to be in quantum computing. Now, you know in your computer right now you have bits, right? And bits are storing your information. So bits have two states. You can think of them on and off, or I think computer scientists call them on a 0 or 1 state. But in a qubit, which would be like what a Josephson junction could do, is you have infinite many states. So instead of just being here or here, you can have different vectors that be like here or here or here or out there. And the advantage of this is you'd have less bits, and you can also superimpose these bits, so one bit can be in multiple states. So this will ultimately hopefully result in faster computers so you can download your internet videos much quicker. And then the other cool thing about it is synchronization. Now, one application of the synchronization is that some electronic circuits are going to use, they need microwave emitters. And if you have Josephson junctions in synchronization, you can emit coherent microwaves, which will be strong enough to use in small circuit applications. So that's another cool thing. And this synchronization has been studied classically, but not quantum mechanically. So that's what we're going for. Now the whole big thing that we're going for is we haven't moved into this new realm of quantum mechanics yet. So we're basically just trying to get down the method of how to run simulations and how to do all that stuff. So a classical analogy of this is to think of it like a pendulum, kind of in a viscous medium. And the big thing about it is, because we're thinking about quantum mechanically, we have to take into account the environment, and it's going to act on the Josephson junction. It's going to apply some damping. So how exactly do you apply damping to a quantum mechanical system? Well, that's where we got this method called quantum jump method. And how that's going to work is there's going to be random interactions with the environment. So the question is, how do you make random interactions occur? Well, first of all, we're going to set up this variable dp, and that's related to the energy quanta of the system, this damping parameter, which we set, and the time steps. So, for larger time steps, there's more likely to be a quantum jump because you have longer time, and if it has more energy, it's more likely to experience a jump. And if you have more damping, it's more likely to experience a jump. Kind of like, more viscous medium, you're more likely to slow down. So once we have this parameter, we make our random number, which I made a special device just for you. It's the Randomatic 3000. And what this thing does is, you just turn the crank here, and it spits out a random number between 0 and 1 out of this bell. And what we're going to do is we're going to compare this random number to dp. And if dp is greater than or equal to the random number, we're going to say a quantum jump occurs. And if not, then we're going to say no jump, and we're just going to continue like nothing happened. Now, if a jump occurs, what we're going to do is we're going to take this Lindblad operator and have it operate on the matrices. And what it's going to do is it's going to take the angular momentum of this pendulum system and drop it down a quantity of h bar. So you can kind of think of it as like there's different levels of energy. And if a quantum jump occurs, you're now down one energy level. So you can kind of see this in this graph. You're kind of going down energy levels. So here's how the actual program is going to work. You're going to start off with a Hamiltonian for this system. And right here you just have a free spinning rotator, which is L squared over 2I. So that's your kinetic energy. Then you add on your potential energy due to gravity right here. And then, since we're physicists, we cheat with Fourier analysis to make it a lot easier for us to do our numerical methods. So here we have our nice Fourier term. And our psi matrix is now going to be represented by this kind of AK matrix, which is going to be changing through time. So here are the operators that we're going to be using. I know you probably can't see them. Check out the PowerPoint slide sections for these operators. So what we're going to do is we're going to have this Schrodinger equation. And we're going to solve it using Runge-Kutta, because we're going to use numerical methods because we can't solve it analytically. So once we do that, we're going to go into a time loop, because we want to see what this thing does as we step through time. So the first thing we're going to ask is, did a quantum jump occur? And if it does, then we're going to collapse the wave function, and that's all she wrote, and then we move on. But if not, and for all things, we're going to always update the AK matrix, because this thing is changing as we're moving through time. It's not staying constant. And then we're also going to finally normalize the vector. And then the result is something like this. So you start out at 16, and then it has these random jumps or kind of stair steps down. And you can see that the stair stepping is more prevalent at the higher energy levels, just like it, because it's related to n. And then once you get down to lower energy levels, it's not as likely to occur, but it still does, and eventually you go to 0. But, you know, that stair-stepping graph isn't very nice looking. So what we're going to do with the program is we're going to average it over a bunch of copies. So that, now we have this nice smooth curve right here. So that's all for our preliminary results, and hopefully we got the method down. Stay tuned for the next episode, and we'll be talking about results and hopefully future work, and maybe we'll see some quantum synchronization. Till then, see ya.